The second half of our chapter on logic is about first-order logic. So to describe what first-order logic is and what it can do, let me begin by saying what propositional calculus, the kind of logic we've been studying so far, can't do. The key point is that propositional calculus doesn't have a way to talk about statements that depend in some way on a variable or on a parameter. And that kind of statement is extremely common in mathematics. For example, in your analysis course that you're taking right now, you would have seen many examples of such statements. Here's a few examples. There exists a rational number x whose square is equal to 2. That is a logical statement, and it depends, the form of the statement depends on a certain parameter, which is this rational number x. And then it asserts that for some rational number x, the square of that rational number is 2. Of course, this is a false statement, but just as our well-formed formulas can be true or false in propositional calculus, first-order logic will be able to represent true and false statements. The next example says, for every natural number n, there exists a natural number m such that m is greater than n. Again, this time we have a statement that depends on two different variables, so an n and an m. And we're saying for all n, there exists an m such that a certain thing is true. For my final example, this is another example from analysis, we have for all real numbers m, there exists a real number n such that for all real numbers x, if x is greater than n, then sine x is greater than m. So you see that these statements can quickly become quite complicated, especially when we have a large number of variables. Here we've got an m and an n and an x, and we're talking about a statement that depends on those three things. If x is greater than n, then sine x, which is some kind of function depending on x, is greater than m. So to study this kind of statement formally, to prove interesting things about it, what we need is first-order logic. When we did propositional calculus, we were able to give a very precise definition of the formal language we used to represent the logical structure of propositions. And that formal language was the language of well-formed formulas. The analogue of a well-formed formula in first-order logic is called a first-order formula. But doing the same thing, so giving a very precise definition of a first-order formula, is rather complex, and we're not going to do it. If you want to see the details, then you can read the book by Derek Goldbrae, which is in the further reading section of the lecture notes, or you can take the Math 0037 in your third year. What we're going to do instead is simply to list the ingredients that go to make up a first-order formula and to discuss the meaning of those ingredients. And then on the final slide in this video, we'll talk about some example first-order formulas corresponding to the statements that I showed you on the last slide. So the ingredients in a first-order formula are quantifiers. So quantifiers have these symbols here, this upside-down A and this backwards E. And the meaning of these things in a first-order formula is that if you have a first-order formula which looks like for all x and then a bunch of stuff, then the interpretation of that formula is that for every x belonging to some specified set, something happens. And equally, a first-order formula that looks like this is interpreted as saying that there exists some element x belonging to some particular set such that something happens. Okay, the next ingredient is the logical connectives and the brackets that we've already seen in our study of propositional calculus. Next we have something new, so variable symbols. Variable symbols are usually lowercase English letters like x, y, and z, and those correspond to a variable or a parameter in a formula, like the x in there exists a rational number x such that x squared equals 2. Finally, the final ingredient in our first-order formulas are relation symbols. And our relation symbols will always be capital English letters like P or Q and R. So relation symbols represent relations. And let me say what a relation is. So a relation on one variable, a one-variable relation, which we write like P of x, is a statement which is true or false that depends on a single thing x, a single parameter x. So a true or false statement about a single thing x. So as an example, you might take something like P of x being x is even. That is a true or false statement about a integer x. Or we might have something like x is greater than 100. That is a true or false statement about an integer or a real number x. Or, I mean, we're not just restricted to numbers here. We might have a one variable relation P of x being x as a triangle, for example. But we don't just restrict ourselves to relations with one variable. We allow any number of variables. So a two variable relation, which we might write as P of x comma y. Again, it's a true or false statement about two things. And you know lots of examples of two variable relations. For example, we might take P of x, y being the relation x is equal to y. That's a true or false statement about two things, x and y. Either they're equal or they're not. So this is true or false. Or we could have x is greater than y. That's a true or false statement about two numbers, x and y. Or we could say x plus y is 100. Again, a statement about two things, x and y, which is either true or false. So that's what we mean by relations. A relation is simply a true or false statement about a certain number of objects of things. So a well-formed formula was just a collection of symbols. It wasn't something that was true or false until we specified a truth assignment. In the same way, a first-order formula on its own is just a collection of symbols. It's not something that's true or false until we say how to interpret it. Once we've given an interpretation, we can then decide whether the first-order formula is true or false in that interpretation. And the same formula will have many, many different interpretations, and in general it will be true in some of them and false in others, just as a well-formed formula might be true under some truth assignments and false under others. So I'm going to give some examples of first-order formulas in the formal language, and then I'm going to give examples of interpretations of those first-order formulas. In fact, these examples are going to correspond to the example first-order statements that we wrote on the second slide in this lecture. So the first formula I want to talk about is this one. So we read this as there exists x such that P of x. So here x is a variable. The backwards E symbol is the quantifier, the existential quantifier this is called, and P is a relation symbol. So an example interpretation of a formula like this would be there exists x in Q, so that is a rational number such that x squared equals 2. And I'm going to say which bit of the formula corresponds to which bit of the interpretation here. So let's just match these things up. So where we say there exists x, that part corresponds to the quantifier exists x. The the fact that x is supposed to be a rational number here is part of the interpretation. That's part of the things that you have to give when you interpret a first-order formula. And then the relation p of x is being interpreted as saying x squared is equal to 2. So that's an example of a simple first-order formula and an interpretation of that first-order formula. This interpretation happens to be false. So let's move on to the next example of a first-order formula here. So this one should be read as, for all n, there exists m such that q of nm. So here, the upside-down a and the backwards e are quantifiers, and q is a two-variable relation symbol. So an interpretation of this first-order formula would be, for all natural numbers n, so we write n is a member of n to mean n is a natural number, there exists m in n. Again, if you haven't seen this funny symbol before, all it means is a member of, so m is a natural number. We'll revise all this in the set theory part of this course, which is coming up next. So such that m is greater than n. Again, let's match up the parts of the interpretation to the parts of the formula. For all n, well, that is this part here. Then the part that says there exists m, that is this part here. And finally, the two-variable relation q is being interpreted as saying that m is greater than n. So q of nm is saying that m is greater than n. So this is an interpretation of a first-order logical formula, and in fact the first-order formula is true in this interpretation. It is true that for every natural number n you can find a bigger natural number m. So natural numbers here just mean whole numbers which are not negative, so 0, 1, 2, 3, 4 and so on. Okay, let's look at the final example then. The final and the most complicated first-order formula that we're going to interpret says, for all m there exists an n such that for all x, p of x and n implies q of x and m. So we have three quantifiers, three variable symbols, m, n and x, and we have two variable relations which are connected by a logical symbol, a logical connective, namely the implies connective. So let's look at an example interpretation. And one possible interpretation is the sentence we saw before, for all real numbers. So I'm going to write this out this time. Real numbers m. There exists a real number n. Such that for all real numbers x, if x is greater than n, then that implies that sine of x, is greater than m. Alright, again, let's match these parts of the interpretation up with the parts of the uninterpreted formula. So we'll take a colour here. The for all m, of course, is corresponding to this bit where we interpret it as saying for all real numbers m. And the next one was exists n. That becomes there exists a real number n. And then we want to say for all real numbers x. So let me get a straight line tool here. For all real numbers x, that's this bit here. Then we have x being greater than n. That's the interpretation of the two-variable relation P. So we're interpreting the two-variable relation P of xn, as being x is greater than n. We then had a logical connective. The logical connective was implies, which we just put into words, and finally our two-variable relation Q of xm got interpreted as meaning that sine of x was greater than m. So these are some examples of how we take of what first-order formulas look like and how we can interpret them as meaningful true or false statements about particular sets of numbers or of other mathematical objects and particular relations between those objects.